Guys, like I said, we're going to do a really quick video that wraps up the calculating the atomic mass of something. So remember that an atomic mass is a weighted average of all of the available isotopes, and the weighting on that average is based on natural abundance. And so it's not an average in the sense that, well, if you have 3 different isotopes, we add them all up and divide them by 3, it's a weighted average. And so the weighting of each component of that average will be based on the natural abundance, and we'll apply a decimal factor to it. We left off last time doing a back of the envelope calculation for hydrogen isotope with just some made up numbers. And so what I want to do now is I want to revisit the calculation for hydrogen with actual numbers that I've gotten from the internet, see how close we actually get to the value on the periodic table. And then I want to do an example for oxygen, and then we should be pretty much good to go with that. You should be able to do that with any isotope that I give you at that point. So let's go ahead and start the screen share, and let's take a look at the information for hydrogen. Now, on the periodic table, the mass in AMU for hydrogen is 1.008. And we made up some numbers last time that were just sort of back of the envelope, but this is a little bit more straightforward. Let me just look up a couple of better numbers here. So, hydrogen 1 has a natural abundance of 99.9885. Hydrogen 2 is 0.0114%. And tritium is actually a trace, 0.001%. And I've fudged just a little bit right there because tritium, hydrogen 3, is actually a trace. It doesn't actually have a percentage assigned with it in most tables, but I wanted to give it a percentage in this table that's as close to reality as possible. And so let's do this example real quick. How do we calculate the atomic mass of something when we're given the natural abundance of each isotope? Remember, the mass number in the symbol represents the number of protons plus the number of neutrons. The value for Z in the symbol represents the number of protons, and it's what identifies the element. If I give you the basic formula for a symbol, remember that X, the symbol for the element, is determined based on whatever the number Z is from the periodic table. Okay, so let's go with that. And so how do I calculate this average mass? Now let's actually give you some masses instead of just using 1, 2, and 3. I want to actually give you the mass in AMU. It's 1.0078, 2.0141, and it's 3 and I'm going to have to make this one up because this data table doesn't actually have it, 3.0022. And so let's go with that. Oh, actually it does. It is given 3.0160. Excellent. Okay, and so let's take a look at how we would do this. Well, remember that the mass is going to equal the average atomic mass equals the mass of the first isotope times its abundance plus the mass of the second isotope times its abundance, so on and so forth. And the abundance is given in decimal form. Ooh. And remember, what's the decimal form of a percentage? Well, if I have 95.00%, in order to turn a decimal into a percent, we multiply by 100. In order to turn a percent into a decimal, we divide by 100. So there's the decimal form of 95%. So let's do this calculation real quick. So I've got the mass for the first component. It's 1.0078 AMU times its abundance, 0.999885, plus the mass of the second one, 2.0141, times the abundance here, which is 0.000114. And let's do the third one. It's 3.0160 times 0.000001. All right, so now what we need to do is just get out a calculator and figure out what all these terms equal. So I'm going to get out my calculator and I'm going to go 1.0078 times 0.999885, and I get 1.0078, or excuse me, 768 AMU plus 2.0141 times 0.000114. I get 0.002296 AMU plus the last term, which will be almost nothing, 0.160 times 0.000001. I get 0.00000. Let me count the zeros. 2, 3, 4, 5. 1, 2, 3, 4, 5, and it's 3016. So now what I do is I take all those terms and I add them together. So I get 1.0079126. And so if I round just to the same number of sig figs on the periodic table, which is 1.008, just to compare, I get 1.008 AMU. Now remember, I'm not applying the sig fig rules correctly based on the calculation we did. I'm just rounding to the same number of sig figs on the periodic table so that we can make a comparison between the two, just so we can see that we did in fact come up with the same value. So this is exactly the same calculation that we did before, but I actually used values that I got from scientific data sources about the natural abundance and the actual masses. What I will point out is that when we talk about the mass of something that's like a proton or a neutron, it's not exactly 1 AMU. It's very close to it. A proton is 1.0078 AMU. But notice that as I add more protons and neutrons, we're getting pretty far away from the idealistic 1, 2, 3, or 4 based on just the number of particles. When I have 1 proton and 1 neutron, we actually had a mass of this one, and I'll rewrite it, 3.0160 AMU for 1 proton plus 2 neutrons. So that's quite a bit different than just 3 when it comes down to it. And so I just want to point out that a proton and a neutron don't weigh exactly 1 AMU. They have a mass that's slightly different than that. And so when you actually look at data for the different isotopic masses of these elements, then you'll see that they're not exactly 1, 2, 3, or some integer whole number. I don't want you to be surprised by that. When we did the calculation last time we were together, we were just using some round numbers to kind of get an idea about how the calculation worked. So now we're actually using real data. We're coming back to it and comparing the value that we get to the value on the periodic table. And you see that we're right on it. And so let's take a look. What I want to do is I want to quickly stop sharing there. I want to share here. And I want to share here. So I looked up some abundances of different elements, and you'll see that the abundances are listed in percentage form. And so this is just from a periodictable.com shout out of these different formulas. If you click on it, you should be able then to look at the individual element, and then you can actually see the mass of that particular isotope. And so what we'll have to do is we'll have to flip back and forth between the abundance, and then I'll click on the element to get its actual mass, and then I'll set up the calculation, and then we'll switch screens. So let's do an example calculation for oxygen. There are 3 isotopes listed for oxygen on this website. Periodictable.com lists oxygen 16, oxygen 17, and oxygen 18 as being the 3 isotopes of oxygen that we can find in nature. 16 being the most, 18 being the second most, and 17 being just a small fraction. And so let me write down the different isotopes on my whiteboard, and then we'll switch back to it in just a second. So oxygen 16 was at 99.757%. Oxygen 17 is at 0.038% abundance. And oxygen 18 is at 0.205% abundance. And now what I do is I'm going to click on each one of those isotopes to get the actual atomic mass of that isotope. And for oxygen 16, it's 1.59949. And I'm going to go with 1.5. I'm going to round up to this digit so that I'm carrying only 1, 2, 3, 4, 6 decimal places at this point. And so let's take a look at that. Now let's move back to the previous screen. Let's go to 17. Oxygen 17 weighs 1.6, and I just said arbitrarily, let's only go with 6 decimal places. So 99913, and I'll round up to 2. And now let's go to the next one, oxygen 18. The mass of that is 17.999161, and these masses are in AMU. So you can go to periodictable.com and you can get this information as well. You can kind of see where I'm getting it from. But what I want to do is switch back to my whiteboard screen, and we can see what I've got written down so far. Okay, so I have the isotopes that were listed, oxygen 16, oxygen 17, oxygen 18. I've got their percent abundance. And I've got their mass listed as well. And so we got this data right from that website, periodictable.com. And so let's go ahead and use this data to calculate the atomic mass of oxygen that we would expect to see on a periodic table, because remember, that's the weighted average. And so let's go ahead and get to that. So oxygen would equal the mass of the first one, so that's 15.994915 AMU. And the decimal version of this is 0.99757. Let's do the next one, 16.999132 AMU times 0.038. Oops, I didn't, two more zeros, 38 plus 17.999161 AMU times 0.00205. Now let's go ahead and have a quick little conversation about sig figs in these problems, because I want you to be able to do the correct number of sig figs when we do these problems. So what I'm going to do is I'm going to do two different answers. The first answer I'm going to get will be the correct number of sig figs based on the calculation. And the second one will be just rounded to 2 decimal places, because that's what you see on the periodic table. Now, on an exam or quiz, I'll probably give you something that has a little bit more sig figs than this, but let's take a look. And this is going to be a multiplication, and so I'm going to be limited by the number of sig figs. Here's the smallest number. I've got 1, 2, 3, 4, 5 there. Same thing here, but in this one, I only have 2 sig figs, where in this one, I have 3. So whatever the answer here is, will be the factor that limits me the most in sig figs. And I'll have to report the number of sig figs in this particular calculation to only 2. And so when I do the addition, the decimal places will be important. So it'll be 2, it'll be 3 here, and I'll be limited to 1, 2, 3, 4. I'll be limited to 5 sig figs here. But remember, we're going to be doing decimals on the next step, so we're going to have to think about that as well. So let's do the first calculation. 15.994915 times 0.99757. So I get 15.956047, and I'm limited to 5. So let me count my 5th significant figure. 1, 2, 3, 4. Here's the sig fig there. And then I'm going to add that to the next calculation, 16.999132 times 0.00038, and my calculator spits out 0.0064567, but I'm limited to 2 sig figs, and so that's right there. All right, let's keep going. I want to do the third term. And the third term is 17.999161 times 0.00205. And I get 0.036898. And I'm limited to 3 sig figs in this place. So there is the sig fig on that one. And now I'm adding them all up. In order to get the average mass of oxygen, I'm adding these up. And so now I need to switch sig fig rules. And now the sig fig rules is number of decimal places. And so let's take a look. I've got 3 decimal places here. It actually turns out that I have 4 decimal places there. And I have 4 decimal places here. So even though it looked like at the beginning, the very first number had the most sig figs and it seemed like it would be the one that would be the least limiting, really in the last calculation, because we're doing it based on the number of decimal places, and these other calculations had to involve very small numbers, it turns out that in my last calculation, I really am using that first set of values to calculate the correct number of sig figs. So my final answer should have 3 decimal places. And so I don't want to round, so I'm just going to add them all up. 0.036898. I'm going to go backwards. 0.0645967 plus the final one, 15.9560474. I get 15.9990405, and then when I round to 3 decimal places, I get 15.999 AMU. And so these are all in AMU. I forgot my units. AMU, AMU. And now if I were to take that and round it to 2 decimal places, just so we can compare it to the periodic table, I get 16.00 AMU. Okay, and so that's how we would calculate the average atomic mass for an element given the isotopic mass and the isotopic abundance. It's fairly straightforward once you've done a couple of these practice problems, but you got to practice in order to be able to sort out the sig figs correctly and be able to just kind of get some practice with the calculation. All right, that's it for that, and that should wrap up that piece.